At this part, we're going to introduce the CAPWAP protocol principles. I think you still remember that in a WLAN between AC and APs, they will establish the CAPWAP terminal. And inside the CAPWAP terminal, we can transmit, for example, control messages and service data. It's developed based on the following four protocols here. First is LWAPP. LWAPP has complete protocol framework. It has defines detailed packet structure and control message elements in multiple aspects. However, the weakness of this protocol is about the security mechanism. The newly formulated security mechanism need to be partial verification. And next is SLAPP. It uses the DTLS technology to encrypt the packets. This is also the highlight of this protocol. Then is CTP and WICOP. Both of them have already achieved the basic requirements of the centralized WLAN structure. However, they have shortcomings in security. For example, the CTP protocol, the authentication and encryption mechanisms are incomplete. And for WICOP, the protocol recommends IPsec and EAP security standards, but do not describe the implementation method in detail. So after understanding these four protocols, actually we should know that the CAPWAP is developed based on LWAPP, or you can think it's an extension of LWAPP, utilize the DTLS technology and add some valuable features of the other three protocols to formulate the CAPWAP we're using nowadays. After knowing the developing background of CAPWAP, then let's see some concepts here. Firstly, CAPWAP consists of two parts. First is a CAPWAP protocol, and the other is a wireless binding protocol. It is generally used in the feed AP and AC solution, and AC manages all APs and delivers control policies to APs through the CAPWAP terminal. Except that CAPWAP packets are encapsulated to UDP packets and transmitted on the layer 3 network. You can see here in this figure, this is AC, and between AC and each AP, they have established the CAPWAP terminal. Inside the CAPWAP terminal, they can transfer, for example, the control message, and they can transmit the service data. Okay, about the establishing process of CAPWAP terminal or the communication process of feed AP and ACs, let's see. This is a procedure. Firstly, we should set up a wired network, including the WLAN, DHCP, routes, and so on. Of course, the wireless network is based on the wired network we have built, right? And then start the AP without configuration. The AP obtains its IP addresses and the gateway IP via DHCP, and obtains the AC's IP address. So in the network, there should be a DHCP server. We can use AC to be the DHCP server, or we can use the switch to be the DHCP server. And after obtaining the IP address, gateway, and AC's IP, then the AP established a CAPWAP terminal with the AC. After the terminal between AP and AC established, the AC delivers the configuration to the AP. And then after obtaining the configuration, AP broadcasts SIDs so that STAs can associate with and access the AP. Okay, so until now, the STAs or the terminals we use has connected to the wireless network. Then let's see how does the WLAN forward packets. The AP converts 802.11 data transmitted from an STA into Ethernet data and forwards the data to the AC through the CAPWAP terminal, and the AC decapsulates the received data forwarded to the wired network, and AC forwards data returned from the WLAN network to AP through CAPWAP terminal, and of course, AP should convert it into a 802.11 format and send it to STA. This is the whole procedure. How does we build or establish a web CAPWAP terminal, and how does the network transmit data, no matter send or receive? Okay, after knowing these parts, then let's see the working mechanism of wireless CAPWAP protocol. AP obtains IP address of AC, and then AP discovers the AC. This state is called discovery, and then it's join. The AP requests to join the AC, and then AP is automatically upgraded. This state is called emit data, and later we will introduce. Actually, this state is optional. Okay, and next is configuration. AC delivers the configuration to the AP, and then data check. AP confirms the configuration, and the last state is run. AP and AC forward data through the CAPWAP terminal. Okay, after knowing the process here, we will introduce them step by step. Okay, then here are the packets that we could use during the whole process. For example, discover, offer, request, ACK, discover request, discover response, and so on. From this page, you can find actually the process is complex. So we will introduce them step by step. The first is DHCP. Because AP is installed, but it do not have any configuration. So at least it should get an IP address. So in this figure, you can find this is a DHCP server, and by exchanging packets between AP and DHCP server, AP can get the IP assigned by the server. So the packets here are discover. So AP will send out a discover packet to find is there a DHCP server exists in this network, right? To discover the DHCP server, and then DHCP server will feed back an offer packet. Pay attention here. Discover packet is sent by broadcast, and offer is unicast. Offer means that okay, I'm answering the request or I'm answering the discover of the AP. Since I'm the DHCP server, and actually in the offer packet, it contains the IP address. So I'm the server, and I will give you an IP address. Okay, and then next step is request. Request means AP has feedback to the server that okay, I know you are the server, and I want to use the IP address you just gave me in the offer packet. And at last is ACK. ACK is acknowledgement. So DHCP server says, okay, you can use the IP address I have assigned to you. Okay, but here I think some of you will get confused. Since in the offer packet, it has already assigned the IP address, so why should I send out the request, right? Or why should the AP send out the request? Because there is a special scenario. For example, this is another DHCP server. This is DHCP server 2. Okay, and the DHCP server will get the discover from AP. At the same time, server 2 can also receive it because it's broadcast, right? Because it's broadcast. So both of them will receive the discover message. And then, of course, DHCP server 2 will feed back an offer. So in this offer is another IP address. For example, this is IP2. And in this case, AP receives 2 IP addresses, but AP only needs 1 IP. So he will confirm that, okay, I will use which one. And normally, AP will use the IP address that it receives first. For example, I received the IP address from DHCP server 2 first, so I will use the IP assigned by server 2. Okay, this is a reason why AP should send a request, because AP will tell the DHCP server 2 that, okay, I will use your IP address to confirm it. And then last step, ACK, right? Acknowledge the allowance. Okay, this is about the packet exchange. And in the DHCP ACK packet, it carries the IP address of AP and the lease time. This is an important concept. Lease means how long you can use it. Normally, the default value is 1 day. It's 1 day. Means server has assigned the IP to the device, to the AP here, and it has limited the time, how long you can use it. For example, you can use it for 1 day, or 2 days, or 3 days. It determines on how do you configure it. Okay, this is called lease. And of course, AP can renew the lease. And then it's the gateway IP, the DS server IP. And the last is option 138. It's an important function of DHCP in the wireless network. Because except getting an IP address, AP should establish the tunnel with AC. So actually, AP should know the IP address of AC. By using option 138, DHCP server can assign or can give the IP address of AC to AP to tell that, for example, AC's IP address is 1.1.1.1. And after knowing that, AP can send some packets to AC to ask for some permissions. For example, if I can establish a tunnel with you, just like this. Okay, this is about the first step, DHCP. And then next step is discovery. Let's see it. The AP discovers the AC using unicast packet. So since it's a unicast packet, it should have a source IP, destination IP, right? And for the source IP, it's easy to understand. It must be the IP address of AP. But for the destination IP, actually it's AC's IP, which is assigned by DHCP server. And then next is discovered by broadcast packets. This is a special scenario. When no AC IP address list is available or no response is received from the unicast packet, AP sends a broadcast packet to discover the AC. Okay, this is a special scenario. And then after receiving the request from the AP, you can see here, AC has already received the DHCP request. So what it should do, let's see. The AC allocates a link ID to the AP and creates an AP state machine control block. The AC switches the status, returns a discover response. You can see here. He will send a response to the AP. And in the response, it carries the DTLS switch status and other information. And then after receiving the discover response from the AC, means the discover state has finished. But if we have multiple ACs in the network, it's possible that one AP can receive multiple response from different ACs, right? So it will choose one. So how does AP determine which to choose? Firstly, AP will compare the AC priority. Which one has a higher priority? So we will choose the AC. But if the AC priority is the same, then we will compare the number of APs connected with the AC. For example, we have two ACs. Right, we have two ACs. This is AC2. And now we have already 10 APs connected with the AC, and we have two APs connect with AC2. Of course, the priority is the same. So in this case, which one do you prefer? Obviously, we prefer the AC with fewer APs, right? Because the working load of it is smaller. Okay, this is a discover state. And then it's a DTLS. And actually, this state is optional. Let's see the function of it. DTLS link establishment process is shown here. To select an AC FSM discover is complete. A DTLS link needs to be established. And the FWD writes a DTLS event called the IPSI API and creates a DTLS link. Through the callback function, the IPSI API sends DTLS link establishment packets. And after the link is established, the IPSI API returns a success event to the FWD. And then the FWD informs the FSM to switch the state machine status. And the function of DTLS actually is to encrypt the packet to ensure the security. CAPWAP control packets starting from the join are encrypted or decrypted using DTLS. Okay, the reason why we say it's optional because you can determine if you should use it. If you do not use it, it will not affect the communication or will not affect the running of the network. Okay, next is the join state. At the join state, first the AP will send a join request to AC. And in the join request message, it carries the AP board, AP software, hardware information, AP's name, kernel packet format, AP's MAC address type, AP wireless information. And after receiving all these messages, AC will verify the blacklist and whitelist first to ensure that if the AP is in the blacklist or not, right? And then AC will confirm the working mode of AP. It's a fat AP or it's a fit AP, right? And then AC will switch the status, returns a join response. And in the response, of course, it's a result, right? It's a result. AC will make a decision based on the information in the join request, right? To determine whether to allow the AP to join, right? If it's allowed or not. Okay, this is the join state. And then next is image data. Because in the former page, in the join states, they have exchanged the version of AP, right, between AP and AC. And sometimes, if the AP version do not match the requirements of AC, actually AP should upgrade the version. Okay, and the state of version upgrade is called the image data. So this is the reason why we say it's optional, because sometimes if the version can satisfy the requirement, we do not need to upgrade, right? And in this state, FSM determines that AP version carried in the join response do not exist in the AP flash memory, and since it do not exist, we should upgrade, right? So the FSM switches to the image data state, informs the LBM to load the AP version online. So after receives the notification, LBM sends and receives image data packets, informs the FSM to maintain the state machine, and informs the FSM to switch the status based on whether loading is successful. If this successful means we have finished the upgrading of the AP version. Okay, and the next state is called configuration. Because AP is a non-configured AP, so it should receive the configuration from the AC. So let's see this state. Firstly, AP send the configuration status request. After the join or image data path is complete, configuration path starts. AP send the configuration status request carrying the AC name, the radio, and other information. And then AP starts the timer. The timer is used to monitor the state, right? And then AC receives the request from AP. It will switch the status, returns a configuration status response to the AP. But you should pay attention here. No configuration is delivered in this path. This is very important. No configuration is delivered in this path. All data is delivered in a unified manner after the run state. Okay, and after receiving the response, AP stops the timer and wait for the configuration status response to timeout. Then switch to the data check state. So let's see the data check state. In the data check state, firstly, in this figure you can find the AP sends a change state event request to AC, and this message carries a radio result code and other information. And at the same time, it will start the timer to monitor the process. And after receiving the request, AC switches to the data check state, returns a change state event response. And then, after receiving the response, AP will stop the timer of waiting for the change state event response to timeout, and AP switches to the run state. So the next run state. Run state actually is very important. Let's see. The AP enters the run state after receiving a change state event response, and AP establishes a data terminal and delivers the data terminal forwarding table. The forwarding table consists of the source IP address, destination IP address, source UDP port, destination UDP port. So actually, you can think this is a table which is used to establish a terminal or to establish the CAPWAP terminal. And then AP starts the keep live packet sending timer, which is 30 seconds. And data terminal detection timeout timer, which is 95 seconds. After the keep live packet sending timer expires, the AP sends the keep live request carrying the session information, which is used for control terminal and data terminal matching. After receiving the keep live request, let's see, AC establishes a data terminal and delivers the data terminal forwarding table. It's actually similar. Source IP, destination IP, source UDP port, destination UDP port, the port number, right? And the AC switches to the run state, runs a keep live response. The AC starts the data terminal detection timeout timer, which is 95 seconds. And then AP resets the data terminal detection timeout timer after receiving the response. So from here, you can know that the same as the name of this message, keep alive is used to monitor the status of the terminal between AP and AC. Once they expire the timer, we will find that there's something wrong or some fault occurs to the terminal between AP and AC. Okay, it's a keep alive mechanism. Okay, after knowing the run state, then let's see at the control plane, how does it work? Okay, you can see firstly AP sends an equal request to AC, right? And it will also start the timer. For example, the equal packet sending timer, which is 30 seconds, the terminal detection timeout timer, which is 94 seconds, right? And then AC will receive the request. After receiving the equal request, of course, AC will switch the state, right? Switch to the run state, and AC starts the control terminal detection timeout timer, which is 95 seconds, which is the same as we have mentioned in the former page, right? The data terminal detection timeout timer. And then AP will receive the equal response. Once received this packet, it will reset the timer. So they can establish the control terminal between AP and AC, and will use the package here to monitor the running status of this terminal. Okay, this is about the working process of CAPWAP, and we have introduced the AP and AC, established the terminal, and after the terminal establishing, how do they send packets. Okay, after introducing the working principle of CAPWAP, let's see a practice question. Is the extension of which protocol? Do you still remember? At the first page of this part, we have said that actually it's an extension of LWAPP. Right, so here we choose A. Okay, that's all for this part.